In the classical and linear world of physics, everything seems predictable. If two light waves meet, they simply pass through one another as if nothing happened. This is the superposition principle, a foundational idea behind many linear equations in physics, including the famous Schrödinger equation, which was formally introduced in 1926 to describe the wave-like behavior of subatomic particles. Schrödinger wrote an equation that explained the wave nature of particles such as electrons. In this linear version, the medium in which the particles move, represented by the potential V, does not depend on the particle itself. The environment is fixed and the particle simply moves through it. For decades, this equation remained one of the most successful theoretical tools of modern physics, helping us understand atomic structures and the quantum world. If we write its time-dependent form, it looks like this. Here, psi is the wave function, I is the imaginary unit, h bar is the reduced Planck constant, m is the mass of the particle, del squared is the Laplacian operator, and v is the potential, and t represents time. This equation tells us how the wave function evolves in space and time. And one of the most important ideas in quantum mechanics is that the directly observable physical quantity usually does not come from psi itself, but from the magnitude squared of the wave function, psi squared. This quantity represents the probability density. But the key point is this. In the linear Schrödinger equation, the potential V does not depend on the wave function itself. In other words, the medium is independent of the wave. The wave is influenced by the environment, but it does not change the environment. Then in the 1960s, the invention of the laser changed everything. The word laser stands for light amplification by stimulated emission of radiation. Suddenly, we had access to light that was so intense, so coherent, and so powerful that matter could no longer remain indifferent to it. This is where physicists encounter something remarkable. Light began to change the very medium through which it was traveling. Imagine a road that bends under the weight of your car. In photonics, when the intensity of light becomes large enough, the refractive index of the material changes. This is often modeled by a relation like, where n0 is the linear refractive index, n2 is the nonlinear coefficient, and I is the optical intensity. This phenomenon is known as the Kerr effect. In other words, light does not merely travel to the medium anymore, it begins to carve its own path. And at that point, the old Schrödinger equation was no longer enough by itself. We needed an equation that could say the behavior of the wave depends on the intensity of the wave itself. And that is how the nonlinear version was born, capable of describing rebellious phenomena such as solitons. Let us begin with the classical version. In the linear Schrödinger equation, the environmental potential V is completely independent of the wave function psi. This means that if we had two valid solutions, then their sum is also a valid solution. Mathematically, if psi1 and psi2 are both solutions, then a psi1 plus b psi2 is also a solution where a and b are constants. This is the superposition principle. That is why in the linear world, waves can easily interfere, overlap, and pass through each other. But in the nonlinear version used in photonics, a magical new term appears, one that depends on the intensity of the wave itself. One of the simplest forms looks like this. Here, alpha is the coefficient related to spreading or wave propagation. Beta measures the strength of the nonlinear effect, and the term psi squared 2 psi is what makes the equation nonlinear. In photonics, this term is often associated with a phenomenon called self-phase modulation. This means that the wave, through its own intensity, changes its own phase. Now the medium is no longer independent. It depends on the wave intensity itself. Mathematically, this creates a feedback loop. The stronger the wave becomes, the more it changes the medium, and the changed medium acts back on the wave. This feedback loop creates an entirely new world of behaviors that do not exist in the linear systems. From a mathematical point of view, this is a profound change, because now the superposition principle no longer holds. If psi1 and psi2 are solutions, then psi1 plus psi2 is not necessarily a solution, and that makes the equation dramatically harder to solve. In most real situations, we turn to numerical methods. One of the most famous of them is the split-step Fourier method. In this method, we split the equation into two parts, the linear part and the nonlinear part. Then we propagate the wave in very small steps, alternately applying the effect of each part. Why is it called Fourier? Because by using the Fourier transform, derivatives in the time domain becomes much simpler in the frequency domain. For example, this makes numerical computation far more efficient. But under special conditions, the equation gives us something extraordinary, the soliton. A soliton is a wave that preserves its shape because of an exact balance between dispersion and nonlinearity. One classical form of a soliton solution is, well, A0 is the pulse amplitude, T0 is the pulse width, sec is the hyperbolic second, and phi 0 is the phase accumulated during propagation. This is the beauty of nonlinear mathematics. Unlike the linear world, where everything tends to spread and decay, here we can build stable structures that preserve information over extremely long distances. The greatest laboratory for the nonlinear Schrödinger equation is a vast network of optical fibers stretching beneath oceans and across continents. Whenever you want to transmit massive amounts of data, like the very video you are watching, you use powerful lasers and optical pulses. And here the nonlinear Schrödinger equation acts as a mathematical roadmap. In photonics, one standard form of this equation is written as, here, A is the complex envelope of the optical pulse, Z is the propagation distance, T is the time in the moving frame of the pulse, beta 2 is the group velocity dispersion GVD. Gamma is the nonlinear coefficient. Now let us interpret this physically. The first term tells us how the pulse changes as it travels along the fiber. The second term describes dispersion. Dispersion means that the different frequency components of the pulse travel at slightly different speeds. And the result is simple. This pulse spreads out over time. The third term describes the nonlinear effect. As we said earlier, this means the intensity of light can influence the phase and behavior of the light itself. Without this equation, a phenomenon like dispersion could completely distort our signals and turn high-speed communication into meaningless noise. One of the most fascinating applications is optical soliton communication. In optical fibers, we can use the nonlinear effect to prevent the pulse from spreading. The result? A wave that can travel thousands of kilometers without changing its shape. That means data transmission with minimal distortion and maximal efficiency. Have you ever seen a nearly monochromatic laser turn into a full rainbow? That is the magic of supercontinuum generation. In this process, a relatively narrow optical spectrum can broaden dramatically after traveling through a nonlinear medium. This happens because of a complex combination of dispersion, self-phase modulation, modulation stability, nonlinear interactions, and the full dynamics described by the NLSE. This phenomenon is extremely important in medical imaging, especially in systems such as optical coherence tomography. In OCT, having a broadband optical source can significantly improve imaging resolution. In the computers of the future, we do not want to convert light into electricity just to switch something on and off. We want light to control light. Using nonlinear effects, one optical pulse can change the refractive index of the medium in such a way that another pulse is deflected, delayed, or redirected. This leads to concepts such as all-optical switching and photonic computing. The future ahead when light begins to think. Today, the world of artificial intelligence, or AI, is hungry for speed and energy efficiency. Silicon chips are heating up and approaching their physical limits. But the future may belong to photonic processors. We are learning how to use nonlinear optical effects to mimic the behavior of neurons in the brain. Inside systems, nonlinear Schrödinger type equations are not just physical descriptions. They can also behave like computational algorithms. Light traveling through a nonlinear medium can, in a very real sense, begin to solve complex mathematical problems in a tiny fraction of a second. One of the most exciting ideas in this area is optical neural networks. In these systems, instead of performing all computation electronically, some part of learning and processing are carried out directly by light. In quantum computing, we seek precise control over particles of light, creating entanglement between photons often requires nonlinear media. And if we can engineer those interactions with sufficient precision, we can build quantum logic gates that operate at the speed of light. The future of photonics also depends on metamaterials are engineered structures that do not naturally occur in this form, and they can exhibit highly unusual optical behavior. When combined with nonlinear effects, they allow us to shape light almost like clay, from ultra-flat lenses to unusual wave steering and even ideas resembling invisibility cloaks. All of these possibilities are rooted in a deep understanding of these equations. The Schrödinger equation began its journey in the heart of the atom, trying to explain what matter really is. But today, its nonlinear version is woven into the very fabric of our digital world. From the messages you send, to precision laser surgery, to high-speed internet, to medical imaging, to supercontinuum, and to supercomputers of the future. All of them are connected in one way or another to the subtle competition between dispersion and nonlinearity. And perhaps the most important message of this entire story is our world is not merely linear, and its beauty lies precisely in that fact. In your opinion, if one day we gain complete control over light, what will be the biggest transformation in human life? Thank you so much for watching. I hope this deep dive into a Schrödinger equation and their engineering application was useful. If you want to explore more about how mathematics fuel modern engineering, make sure to subscribe to our YouTube channel and hit the notification bell. For more in-depth tutorials, technical articles, and resources, don't forget to visit our website. We have a lot more exciting content coming your way. See you in the next video.